In off-grid microgrids, renewable generation introduces low inertia and frequent frequency excursions. Conventional battery storage can stabilize the grid, but it's often too expensive for remote communities, constraining reliable energy access. Virtual energy storage systems offer a cost-effective path by treating flexible loads, like HVAC, as virtual batteries to balance supply and demand. We address this gap with a virtual asynchronous machine, VAM-based distributed secondary control that lifts microgrid stability and reliability. Our solution uses a two-layer architecture. First, VAM-based primary control at each VESS makes the resource behave like a source with virtual inertia and damping, enabling rapid power modulation for frequency support. Second, a distributed secondary control coordinates all VESS units to remove steady-state frequency error and enforce proportional active power sharing. It requires only local measurements and neighbor-to-neighbor communication, no centralized controller. To simplify design, the nonlinear VAM dynamics are embedded into a linear reference model, and Lyapunov analysis guarantees convergence, even with communication delays or packet loss. Each VESS is modeled with a unified electrothermal building model, capturing heat transfer through walls, windows, and roof, solar gains, ventilation, and heating/cooling dynamics. By modulating heating or cooling within comfort limits, a building charges or discharges heat like a battery, assisting grid balance without sacrificing comfort. We demonstrate the approach on an islanded microgrid with 4 VESS-equipped houses, about 45 kilowatts of generation, and an 18 kilowatt baseload. Each house initially supplies roughly 10 kilowatts of heating, and all units communicate over a lightweight network for secondary coordination. Simulations confirm effectiveness. Under a load disturbance, the microgrid frequency returns to 50 Hz within about 3 seconds and stays within plus or minus 0.1 Hz, faster and tighter than standard expectations. The VESS fleet shares active power proportionally to ratings, demonstrating accurate power sharing behavior. With impaired communications, the controller remains robust. Even at 30% packet loss and 100 milliseconds delay, the system still converges to the correct frequency and sharing targets. In 24-hour winter-dark-summer runs, indoor temperatures stay within typical comfort ranges, deviating by less than approximately 0.8 degrees Celsius, showing that grid support does not compromise occupant comfort. By leveraging flexible demand as virtual storage, communities can reduce dependence on costly batteries and lower microgrid costs. The scheme is scalable, community-oriented, and operable with basic training, supporting clinics, schools, and households in remote or weak grid regions,